I am. I'm going to attempt your questions bit by bit, I'm afraid. Some of them are very, very complicated, and I don't want to do a video that's too long. Okay. So let's try and attack one and two for now. Maybe you know the answers to these ones, because these ones aren't very hard. All right. First of all, which statement about molecular geometry is incorrect? So we want the wrong one, according to Vesper theory. And as you know, I'm sure, Vesper, if I can remember it, stands for valence shell electron repulsion. I don't know, electron pair. I wonder what the P was. Electron pair repulsion. Okay. And basically, it's very simple. It means electrons move away, maximize distance from each other to minimize repulsion. That's all it means. Okay. But they've asked obviously tricky questions here, and you've got to figure out which one's wrong. Electrons in lone pairs take up more volume than electrons in bonds. So what that means is if you have, let's say, let's have a look at ammonia, for example. There's ammonia molecule. Okay, now, and there's a lone pair on the top, and these are bonding pairs here, here, and here. So electrons in lone pairs, this is the lone pair, and these are known as bonding pairs, take up more volume than electrons in bonds and will cause a bond angle to be compressed. Now, let's compare that with methane. This is methane. Okay, so all of these are bonding pairs. Okay, but in the case of ammonia, there's one lone pair. So what that does is, as it says, lone pairs take up more volume. So they're also closer to the parent atom. So let's get a different color. We've got two colors here. So let's pick this color. These are closer to the parent atom. These are pulled further away. So these push down and decrease these bond angles. In methane, the bond angle is 109.5. But in ammonia, it will be about 107. It will be squashed down. So the lone pairs repel more than the bonding pairs. And volume thing is one reason for the increased repulsion. And the second one is it's closer to the parent atom, so it pushes down more. So this is a true statement, so it's wrong answer. A central atom bearing two lone pairs, so let's draw that. Central atom, there it is. It's got two lone pairs, one, two. Where are we? Central atom and three other atoms will have a trigonal planar geometry. Right, now, if it's got one atom, there's one atom, two atoms, three atoms. Trigonal planar means it will be like this. All the angles are 120, and it's in a plane. Okay. Now, because of these lone pairs, it's going to squash these, and it's going to form a pyramid shape, just like ammonia, actually. It's going to form a triangular pyramid shape. Okay, this thing, because the lone pairs are going to push down. So they're not going to be in the same plane. So this sentence is wrong. So therefore, it is the right answer. So it's this one. It's not going to be trigonal planar. It's not going to be planar because the lone pairs are going to push the bonding pairs down. All right, and it's not going to be planar. Let's check the other ones. Tetrahedral geometry is preferred over square planar for a central atom bonded to four carbons with no lone pairs. Yeah, if you've got something like methane there, all right, this would be square planar, but it doesn't take that orientation. It takes tetrahedral, doesn't it? All right, and neither have lone pairs here. Here, if you think about it, the repulsion is not minimized because that's a bond angle of 90, but they can get further away from each other in a tetrahedral. Okay, so this one is preferred. So that is a true statement. Central atom bearing two lone pairs and four other atoms will have a square planar geometry. Yeah, that's true as well. Let's think of something like, can't think of anything. I'm going to guess one here. Sulfur, fluoride. Okay. There's sulfur. This is sulfur. I'm drawing sulfur hexafluoride. Okay. Now, let's remove two of these fluorides. Let's remove that one and that one. And instead put, this doesn't exist by the way, I'm just showing you. Let's put the two lone pairs there where they would have been. Now, the top lone pair will push these bonds down, but the bottom lone pair will push these bonds up, and it will end up as a planar pattern. All right, and it's known as a square planar. Well, that's not very good. So this is correct as well. Okay, so the answer is 1. I don't know what you call that, 1B, I guess. I don't know. For which reaction is Kc equal to Kp? Okay, now when you use Kc, Kc is all about equilibria in concentrations. Okay, and Kp is when we use it for partial pressures. Okay, I just spell pressure. There you go. Now, for a gas, the concentration, if I increase the concentration of a gas, it is directly proportional to the partial pressure. So if I double the concentration, the partial pressure doubles. They're not equal to each other, but they're certainly linked to each other. Okay, so but what I'm trying to say about that is this: if you've got a concentration of A divided by concentration of B times a concentration of C, it's going to equal the partial pressure of A divided by the partial pressure of B times the partial pressure of C. The concentration of A isn't equal to the pressure of A, but they're what's the word we use? They're that word. They're related. They're proportional to each other, aren't they? Gosh, I don't know what's going on. So even though the concentration isn't equal to the partial pressure, the ratios will be equal. Ratios are equal. Okay, so we've got to find somewhere where the ratios are going to be the same. If the ratios are the same, the concentration of the partial pressure is going to be the same. Okay, so let's go through. First one, where am I going to draw this? Let me get rid of some of this rubbish. Okay, I hope that makes sense. I'm sure your lecturers are a lot better these days, but I'm just doing my best. Whoopsie daisy. Whoops, where are we? Well, this didn't work, did it? So I hope things are going well while I'm messing this up. That side. Okay, there we are. Let's get rid of this rubbish. I'm amazed that you've done so much, by the way. It's only November. You seem to have done loads. Right, now let's have a look at this one. Let's have a look at, I'll call them A, B, C, D, and E. A, this one, let's have a look at the Kc for that one. Kc for that one is just the concentration of the carbon dioxide, because we don't put solids in these things because solids don't have concentration, so it's only that. So Kc equals that. Kp will equal the partial pressure of the carbon dioxide. Now they're not the same as each other. Okay, all right, so that one's wrong. Number 2, the Kc is going to equal carbon dioxide, the concentration of carbon dioxide, divided by the concentration of carbon monoxide squared. Okay, so there's that. We ignore the carbon there because it's a solid. Okay, now the partial pressure is equal to, what are we? Partial pressure of carbon dioxide divided by the partial pressure of carbon monoxide squared. Now, these, because these there's going to be units here. This is concentration by concentration squared, and this is pressure divided by pressure squared. Kc and Kp are not going to be the same, okay? Because they're not unitless. They do have units, okay? So they can't possibly be the same, can they? All right. So let's have a look at C. Kc for C is HF, concentration of HF, divided by the concentration of hydrogen times the concentration of fluorine. Now, look at this. This is unitless, isn't it? Because everything cancels out. Unitless. And if I did the Kp, it's the partial pressure of HF divided by the partial pressure of hydrogen times the partial pressure of fluorine. And this is unitless as well. Okay, so in this case, and look, everything is a ratio, and they're going to cancel. The ratio will be the same. It's like saying 2 is equal to some constant times, I don't know, let's say 12 is equal to some constant times 3. Okay, Therefore, what's the constant here? The constant is 12 over 3. It's k, isn't it? So, so let's do another one. 12 is to 3 as, I don't know, 6 is to 1.5. The 3 over 12 is equal to 1.5 over 6, isn't it? So even though the numbers aren't the same, their ratios are the same. Okay, that's the kind of idea I'm trying to get across. I don't think I've explained this very well at all. It's been a long day. I'm going to stop the video there, send it to you, and I'm going to work on the other ones. All right. Okay, hope things are going good. See you later.